Okay, welcome everybody. I just wanted to go back over single replacement reactions real quick. So we just finished the single replacement reactions lab, and in this lab we noticed that not every metal will react with every metal solution. Single replacement reactions do not happen 100% of the time, and we have to be able to predict when they're going to happen and when they're not going to happen. If you guys did not write equations for the reactions that you observed on Friday, then you need to make sure that you do that. The back of this sheet, the data analysis here, needs to be done. I can do one of them with you just as an example. You guys should have noticed that silver nitrate did react with copper in the lab. When these things react, what's happening is the single element is replacing the element that it is most similar to in the compound. So the two similar elements are going to switch places. In this case, if we took copper metal and put it into silver nitrate, it's going to switch places with the other metal, silver. So on the back, I'm going to write an equation. Copper metal was placed into silver nitrate. These are my reactants because those are what I put in the test tube, okay? And what's going to happen is the two metals switch places. So copper is going to end up with nitrate and silver is going to end up by itself, okay? But before I can just write CuNO3, I have to check charges. So nitrate is a polyatomic ion, and on the back of the periodic table, it's listed here, with a charge of -1. So I'm combining nitrate with a charge of -1 and copper with a charge of +2. How do I know it's +2? Told me so on the front, okay? So this will be copper 2 nitrate whenever we're done with it, okay? 2 plus and 1 minus are not going to cancel each other out. So in order to get the charges to cancel each other out, because positive and negative energy has to cancel each other out, I'm going to have to crisscross, if you guys remember. I'm going to have to double the amount of nitrate that's in here. So to balance charge, we are going to use a subscript. We're going to double nitrate. So I'm going to put it in parentheses and then put the subscript 2. Okay, so that balances the charge. But it changes the amount of nitrate I have on that side of the equation. I can't start with 1 nitrate and end up with 2. That's the law of conservation of matter. So I have to use a coefficient then to balance the amount of each substance on both sides. So subscripts are used to balance charge. Coefficients are used to balance amounts on both sides. If I doubled nitrate, I have to double it here. Now that also doubled my silver, so I have to double that here. So this now is the balanced equation for the single replacement reaction that happened between copper and silver nitrate, okay? But you'll notice that a lot of times in this lab, these reactions did not go through. In fact, we could put the metals in order and create what we call an activity series, okay? In an activity series, the most reactive metal goes here, and the least reactive metal goes here, okay? What is a most reactive metal? Most reactive metals want to be in a compound. And least reactive metals want to be single. Okay, they don't want to be in a compound, they want to be the single lady. So if I look back at this, if I look at the data for the lab, you guys probably noticed that copper reacted 1 time. Magnesium reacted several times. It reacted here, here, and here. Nickel didn't react, right? The nickel ball didn't react with anything. And then zinc reacted twice. It reacted with the copper sulfate and the silver nitrate. Okay, so that's what you guys should have noticed in the lab. There were 6 different reactions that occurred, but a lot of times it didn't. Okay, and again, that's due to the activity of the metals. Some of them are just more reactive than others. Okay, magnesium reacted 3 times out of 5, and nickel did not react at all. So in my activity series, based on my data, magnesium would be at the top because it is most likely to react and form a compound. Whereas nickel reacted the least often and was most likely to remain single, to not form a compound. Okay? And then I believe it was zinc and then copper, right? So zinc and then copper. Okay? This is how an activity series works, and it allows me to predict when a reaction is or is not going to happen. And you guys have one on the back of your periodic table. Okay, again, up at the top, these elements are most likely to form a compound. So if they're not in a compound, they want to be in a compound. Okay? And these guys down at the bottom, if they're not in a compound, they're just fine. They want to remain single. And if you notice, my least reactive elements, the ones that want to remain single most often, are silver, platinum, and gold. What are those three used for? They're used for jewelry, right? Which makes sense. You don't want your jewelry to be reactive. You don't want it to react with your skin, okay? So the things that want to remain not part of a compound, that want to remain metal, they're at the bottom. Up at the top, you'll see metals like lithium and potassium. These are alkali earth metals, okay? And we already talked about how they're highly reactive, and that's why they're at the top of the activity series. If these are being added to a solution, that reaction is probably going to go forward, okay? So you guys should have a worksheet that looks like this. And this is practice predicting when these reactions are going to go forward and when no reaction is going to happen, okay? Because that's a possibility too. By the way, the halogens are already arranged kind of like an activity series. So if I look at the halogens right here, this is my halogen family. The most reactive element is fluorine, and the least is astatine, okay? So if I'm adding fluorine to a solution, fluorine wants to be in the compound, it's gonna react. If I'm adding astatine, then probably not, okay? So again, we'll use this information. I'll do a couple of examples with you. So looking at number 1, I've been given aluminum bromide and chlorine. So aluminum bromide is Al, and if I check the charge on that, aluminum always gets a charge of +3. And then bromide is bromine, and that gets a charge of -1. So if I have aluminum with a 3+ charge and bromine with a 1- charge, it would take 3 bromines to cancel out aluminum's charge. Okay, if I crisscross it, that 3 is going to go right there and tell me that 3 bromines have to be attached to aluminum. So this is AlBr3 plus chlorine, which is a diatomic element. And if you don't remember the diatomics, there's a little saying, have no fear of ice cold beer. Those are my diatomic elements, okay? Most of them are gases, and they naturally occur in their elemental form as a diatomic. Di means 2, so they roll in pairs, okay? Back to this. Now that I've written the formulas for my reactants, I need to think about it for a second. I'm adding chlorine to this compound. First off, what is chlorine going to switch places with? What's most like chlorine? Chlorine is a nonmetal, so it's going to switch places with the other nonmetal. It's going to switch places with bromine. Okay, so those two things are going to switch places. Or are they? Let me check my activity series real quick. Let's see if this is even going to happen. Okay, well, chlorine is more reactive than bromine, which means chlorine is the one that has the greater desire to be in a compound. Okay, so chlorine wants to be in the compound. Is it in the compound right now? No. So let's put it in the compound. Okay, again, bromine was one of my diatomics, so I'm going to make sure that I leave it Br2 there in the equation, okay? So yes, this reaction would go forward, And here are the products that would form. Okay, aluminum chloride and bromine. It's not balanced. We need to put coefficients there. Okay, so if I think about it, bromine, there's 3 of them in the reactants, but only 2 in the products. And I can't multiply 2 by anything to get 3, but I could multiply both of these numbers and get 6. So if I put a 2 here, that gives me 6 bromines on that side. If I put a 3 here, that gives me 6 bromines on the product side. I could do the same thing. If I look here, I know I'm going to need 2 aluminums. That gives me 6 chloride ions. To get 6 chlorines in my reactants, I'm going to put a 3 right here. So this is the balanced equation, okay? This one would go forward, and this would be the balanced equation for it, okay? Let's go ahead and look at number 2, okay? If I look at number 2, I've got silver. The formula for silver is Ag, okay? And then sulfuric acid. Ooh, writing formulas for acids. Terrible. There's no hydro prefix, so it comes from a polyatomic ion. Sulfuric acid contains the sulfate ion. It is H2SO4. Okay? And you may be thinking, okay, well, silver has to switch places with another metal. But there's no metals in sulfuric acid. But remember, hydrogen is in a family with all metals. It's in that alkali metal family. And so if silver is going to react with sulfuric acid, it would switch places with hydrogen. Okay? Is this reaction going to happen or not? Well, let's look at the activity series. Okay? If I look at the activity series and I compare silver and hydrogen. Okay, let me compare. Here's silver way down at the bottom like we said it was going to be. Okay? And then hydrogen is above it. What does that mean? Hydrogen has the greater desire to be in the compound. Okay, so the one at the top wants to be in the compound. Look at that, it already is. It's already in the compound. So if hydrogen is the more reactive element of the two, and it's already in the compound, then no reaction is going to take place. Okay, that's the way that this works. You compare the two elements that are similar. The one that is higher up on the activity series is the one that needs to be in the compound. If it already is, then no reaction is going to occur. Things are already the way that they want to be. If it's not, however, you need to switch those two elements so that the more reactive one is in the compound and the less reactive one is left single, like we did right here. Okay? So good luck with the rest of this worksheet, and I'll see you soon. Bye.